Hi, I'm Ben-Yaakov. This presentation is entitled "A User-Friendly Basic Design Method of an LLC Converter." In this presentation, I'm going to give a very short background on LLC converters, the fundamentals of the new design method, which I believe is much simpler than what is usually considered as the classical approach, show the design step, and essentially give a design guidelines. We are concerned here with an LLC converter. I'm showing here it in a half-bridge configuration. Here are the two inductors, capacitor, transformer, rectifier. This is the filter capacitor, and this resistor represents the load. Now, the problem that we are usually faced in the design of this LLC is the following. We have a range of input voltages between some maximum and minimum. We might require a certain range of output voltage, although sometimes it could be a fixed voltage, but in general we may wish to have a range, like battery charging, for example. And then we have a range of current that we might wish to have. And of course, we'd like to work at a given region of a switching frequency, depending on the transformer, switching losses, etc. Now, the unit could be in a half-bridge or full-bridge configuration. The design that I'm talking about is actually related to the full bridge, and for the half-bridge, one has to take into account that the effective voltage is half of the full-bridge configuration. So this is given, and this is what we have to find. We have to find what is the resonant, L sub R, L sub M, C sub R, and the ratio, the turns ratio of the transformer. This is what is required. Now, usually, customary, I should say, very popular, we are faced with this type of a curve. We see here a normalized frequency, and then we have gains, input to output, for given quality factors. And here I've marked two of them, like 0.5 and 0.1. And this is the gain that you'll get for this quality factor. Now, as it turns out, this quality factor is related to the LR and CR. These are the two elements. And then you have to wrestle with these curves and plots in order to get what you need in terms of the actual value of the resonant inductors and capacitor and the turns ratio. I've shown in an earlier video that in fact we have two quality factors that we can think about or talk about. One is the series one and one is the parallel one, which is actually responsible for this gain. But in this presentation, I'm going to forget about this parallel thing and just stick to what is very popular today, and then using this quality factor, which is defined here as the characteristic impedance of L sub R, C sub R over RE, when RE is the equivalent resistance. I'll talk about it in a minute. So I'm going to relate to this. I'm going also to use the first harmonic approximation and also the concept of RAC, in which we are replacing the nonlinear part by an equivalent resistor such that the loading will be the same. In fact, the Q will be the same. And this is was presented, of course, by Professor Steigerwald, the first presentation of this concept. And this is the relationship of RE and the actual RL. And what we have here is a constant and also this turns ratio of the transformer. So I'm going to use this to represent the actual LLC converter. And of course, from RE, you can go back and find what is RL, or the other way around. If you know RL, then you know what is the RE that you need. So let's start with very basic relationship. Q is Z over RE, and Z is the square root of LR sub CR. Also, you can define the Q as omega 0, which is the resonant frequency, LR over RE, where the resonant frequency is 1 over LRCR, And again, this is related to the smaller inductor. It turns out that Lm is a larger inductor. In fact, the ratio between the two is defined as m. And then the resonant frequency is, of course, 1 over 2 pi and this square root. And I've already shown this relationship. And m is defined as these two. So these are the very, very basic relationship that we're going to use later on. Now the question is, what should be Lm? That is the ratio between Lm, L sub m, and L sub r. These are these two inductors. As it turns out, this ratio has an effect on the response, on the gain response. And as we can see here, for m equal to 10, we have a broader response, lower gain. This is for the same Q, for the same quality factor values. And therefore, in this case, we'll need a larger span of frequency, while here, the span of frequency is small, but then the Q is high. Now, we know that a high Q is causing high losses because a lot of reactive energy is circulating in the circuit. So from the loss point of view, this is not very good. This is not very good due to the large span of frequencies that you need. And experience has shown that m equal to 6 is kind of a good number. Now, obviously, one can go and design the circuit, do simulation, and then do some iteration with the m, find out maybe a better value for m. I'm going to stick at this point to 6. Really doesn't matter. I'm just assuming this is the number that I've decided on in this design. So what is the plan here that I'm going to show? This is what is now used. The classical approach. We are looking at these and finding out what is the region we would like to work at, etc., etc. I'm going to sort of turn things around, and I'm going to talk about resistances, because obviously Q is related to resistance. Here it is, it's Z over the resistance, the equivalent resistance. And the problem with the Q is that the resistance is 1 over. We are used to resistances, so Q is kind of becoming a little bit mysterious here. We don't know how to deal with it. So the approach that I'm developing here is based on resistances. That is, I'm going to describe this gain plots by resistances. Each one of these corresponds to a resistance. Now there is a characteristic impedance involved here, so I'm normalizing everything to Z equal to 1. And also normalizing the frequency to 1. So this is the normalized frequency, and also Z is normalized to 1. I can run simulation to generate such a plot, and this will be done by choosing C sub r and L sub r of same value, so Z is equal to 1. This is the ratio between them. And also choosing the C sub r times L sub r through the frequency equation to be 1 hertz. So I'm going to have a resonant frequency of 1 hertz. This is for CR and LR. And a Z of 1 ohm. So this is the normalization. So this resistor is now a normalized resistor. That's not the finite resistance. I'm going later on to relate it to the actual resistance. Once I do this, here is the plot that I'm getting. Again, this is normalized to Z equals to 1. And here are the normalized resistances. I see that the normalized resistance of 0.1 ohm gives me this type of a gain. And then as this resistance goes up, the gain is becoming larger. Now, this is a universal curve, okay, for Z equal to 1. Now, the nice thing about LLC, of course, that all these resistances are actually converging to this one point with a gain of 1. So this is very nice, and this is why we like to work in this area, because then it will be insensitive, the converter will be insensitive to the load resistance. So in order to explain the approach that I'm proposing here, let me start with a simple case not to complicate things at the beginning. And I'm assuming that the input voltage is changing between some Vin max to Vin minimum, and then assume that the output voltage is constant and the current at the output is constant, and I need a certain switching frequency. So this is given. Later on we'll show what you do if these also are changing. So in this case, what I like to do is, first of all, for the nominal voltage to work here, because this is a very good point. So I want this to be a gain of 1 for the nominal voltage. Now, if the voltage is dropping at the input, I need gain. And how much gain do I need? I need the ratio of the Vin max to Vin minimum. And this is an example of 2. That is, the ratio between the maximum voltage and the minimum voltage is 2, so that if the voltage drops, I can go up here, increase the gain, so as to keep the output voltage constant. So if I look now at these curves, clearly there's only 2 curves here that will actually satisfy the requirement of a gain of 2. These are not satisfying this requirement. They will not go, these normalized resistances will not go up to a gain of 2. So I can choose either of 1, and obviously I don't need that much of a gain, so I'll choose the value of 5 for the normalized resistance. So now I'm taking it out, and this is all that I need. I don't need all the other curves. I need this one, which is telling me that if the normalized resistance is 5, then I can get a gain of 1 at 1 hertz, normalized frequency, and at this frequency, which is what, 2, 3, about 0.4 hertz, 400 millihertz, I'll get a gain of 2. There is some spare here, I can get a little bit more, and in fact I can also get some attenuation. That is, if the input voltage is actually a little bit higher than the nominal, then I can actually do some attenuation. So this is the curve that I'm going to work with. That is all that I need. I don't need any of the other curves. So now, just knowing this single normalized resistance of 5, which I've chosen for this particular problem of a gain of 2, I can actually calculate everything. So I'm starting with the power, which is the output current times the output voltage. Of course, I can put here the efficiency to relate it to the input, but I'm not doing it here. So power is also the voltage times RE. RE is the equivalent resistance. This is the resistance. And at resonance, the full voltage is imposed on the input. Of course, here it's half VCC because it's a half bridge. So from here I can get what is the RE. This is Vin max over P, which I know. Now Q is defined as Z over R. It is very important to realize that although I am dealing with R, normalized resistance, the curves are actually representing fixed Q. So I have to keep the same quality factor. And I'm now relating the quality factor of this normalized circuit, in which Z sub n is 1 and R sub n is 5, to what I need in reality, which is a Z which I don't know. I'm going to calculate it, and RE I already know what it is. From here I'm calculating the characteristic impedance needed in the real system. Once I have it, dividing Z by omega 0, dividing this, you can actually get L sub R, okay? C sub R is divided out. So we get L sub R. So already now we get one parameter that we need. Now, knowing the resonant frequency that we want, I can calculate C sub R. So this is the second one. Knowing M, I can calculate Lm. So this is the third one. Now I know that RL, that is the real resistance at the output, is V out over I out. This is related to R sub E, the AC resistance by the Steigerwald equation. So I can calculate the fourth parameter, which is the turns ratio of the transformer. That's it. So let's see now just a numerical example here, okay? Suppose I want the frequency, resonant frequency, to be 100 kilohertz. V in max is 400 volt, V in min is 200 volt, the ratio is 2. Output is 100 volt. Current is 10 amp, so the power is 1 kilowatt. And since I need a ratio of 2, I know that I need the normalized resistance of 5. So now I'm starting to calculate RE, which is V max square over the power, 160 ohm. I find what is Z as RE over 5. This is the normalized resistance, because the normalized characteristic impedance is 1. So this is the expression for the actual Z that I need in the system, which is 32 ohms. From here, dividing the Z by omega 0, I get L sub R. And knowing the resonant frequency, I can get C sub R. And since I've decided about M, I'm getting L sub M. So that's it. That's the whole thing. I don't need anything more than that. Let's see how good is it. So I'm going to run here a simulation with the values that I've found. Okay? This is the 160 R sub E. Of course, I can relate it to R sub L with the rectifier, etc., which I'm not going to do. So I'm going to stick to this first harmonic approximation, the RAC approach. And when I do that, here's what I'm getting. At 100 kilohertz, the gain is 1. And at a lower frequency, I get a higher gain, up to 2 and a little bit more, exactly what I've seen before, except that now it's not normalized. This is now the real values that I need. So that's it. That's the end of the design. If, however, I also would like to accommodate a change at the output voltage and output current. So I'm given these, and again I have to find these values, which I did before, for a case that the V out was constant and I out was constant. So the first thing to do is to realize that since the gain that I need is related to the normalized resistance, so it really doesn't matter. I have to choose a normalized resistance, and if the ratio is 2, the choice is 5. This is a universal choice. I mean, that's it. The question is, what is RE? Because I need RE, R sub E, in order to do all the calculation back to the parameters. Now, looking at this curve, we see that there is no problem for the system to give us gain when the resistance is high, the normalized or the real one, okay? So I have to make sure that for the smallest resistance, I'll have sufficient gain. So if I've chosen R sub n to be 5 because I need a gain of 2, this should be related to the smallest resistance in the circuit that I'm expecting. So what will be the smallest resistance? It will be the smallest voltage and the highest current. This ratio is related to the smallest resistance expected in the system. So therefore, When calculating R sub E, I'm going to take V in over P related to these two. That is V out minimum times I out maximum. This is reflecting the case of the smallest resistance. And therefore, this will be the smallest resistance that I'm expecting in the real system. V in max over this power, and this is of course for the maximum voltage. If the voltage is minimum, I have gain. So I'm not talking about this, I'm talking about the situation that the gain is 1. For the gain 1, the output voltage on R sub E is V in max, and this is the power expected for the case of the smallest RE. So then I'll go through the same, I'm going through the same calculation, except that RE has been chosen differently, because this P has been chosen differently. Everything else is the same, and I'll get all these values as I did before. So this brings me to the end of this short presentation. Well, it is short because, as it turns out, if you look at it this way through the normalized resistance, things seem to be much simpler that at least I used to look at the problem. So thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.